Okay, sorry for this. So I'm going to talk about some new ideas about variational inference and its application for generative adversarial learning. So when we use variational inference, we minimize the KL divergence. So P is the target distribution, often it's a posterior distribution they want to approximate, and we want to find the optimal Q by minimizing the KL divergence. Often what's happening is you are going to set up a family, parametric family of Q, and because of Q divergence, one of the major restrictions is that we need to actually make sure Q includes only densities that you can actually calculate log Q or its derivative, because this is one of the requirements for optimizing Q divergence. Now this talk is about new ways to do variational inference without requiring to calculating log Q, and we coined this type of method as wild variational inference. So I'm going to first talk about what's called Stein variational gradient descent, which is a poster in this NIPS that finds a set of particles by, in some sense, explicitly minimizing the KL divergence. And then I will use the idea of Amortized, so training another neural network sort of to mimic the particle dynamics. In this way, you can actually train arbitrary neural network or any function that you can backpropagate to learn to draw samples from distribution. And then I will use this idea to amortize max molecular tuning for energy models, and we get something that is quite similar and almost as good as GAN-style methods. So some basic ideas about Stein variational gradient descent. So the idea is we want to find a set of particles to approximate the posterior distribution. So we do this iteratively. So starting from a set of particles drawn from some simple distribution, right? And then we iteratively apply incremental updates. So in this formula, epsilon is a step size, phi is a perturbation function, and it's choosing to optimize sort of the decreasing rate of KL divergence. So in the formula below, Q prime is the density of the updated formula, and you want to choose phi to maximize the negative slope, decreasing rate of KL divergence. So this actually frames a functional grid optimization, which has infinite dimension. But what's surprising is that it actually has a closed form solution. It's actually a simple problem to solve. So it turns out the objective function, without going into much detail, you can actually do the derivation by yourself. This gradient of KL divergence is actually a linear functional of the perturbation function phi. So it actually relates to something called a Stein operator, which again relates to generator of non-joint diffusion processes. I'm not going into much detail, but it also relates to what's called the Stein's identity that essentially says that when P equal to Q, this gradient actually equal to 0, which is sort of obvious, but typically this Stein identity is derived using integration by parts. So now it's a linear functional. If we can further define the function set phi, the function set, the set of possible perturbation direction you consider to be in the uniball of a reproducing kernel Hilbert space, then you are essentially having a linear optimization, maximizing linear function in a uniball, and this obviously have a closed form solution, like in finite dimension, it's trivial. For infinite dimension, it's essentially the same thing. So you can solve this problem. So this optimal value is something called kernelized Stein discrepancy that we derived recently. But it's rooted from what's called Stein's methods in theoretical statistics. So essentially, this is our algorithm. So this big, complex, relatively complex formula is the optimal perturbation direction we derived. So basically, this is a dynamic that allows you to transport a set of particles from arbitrary density function. Actually, you don't need to know the initial density function to the target distribution. So just give a closer look at this formula. It has two terms. The particles are driven by, in one hand, by the gradient information. The gradient information forces the particle to move towards the high probability region of the posterior probability. And we also have a repulsive force that enforces the particles to be different from each other. So this is what Bayesian requires, is to get a diverse particles to have a nice quadrature approximation, right? So in this demo, you can see that the particles are initialized far away from the distribution, and because of the repulsive force, it can actually escape some of the local minimums and eventually achieves a very nice quadrature approximation for the posterior distribution, for the target distribution. In this case, it's a Gaussian mixture. So this is the same thing, except we use more particles and we visualize it using density estimation. So one of the nice property of this algorithm that I really liked is that if you only use one single particle, then it's exactly maximum, like it's exactly gradient ascent for maximum A posterior. So it will find one of the mode. So now by using more particles, you actually have a very nice smooth between gradient ascent for point estimation, finding the mode, to a full Bayesian estimation. So adding more particles that are diverse allows you to evaluate the uncertainty in a Bayesian fashion. So it turns out if you actually take n equal to infinite and also take the step size to be 0, then the limit density of the particles is going to be captured by some PDE. It's actually a nonlinear PDE. But turns out this PDE is actually equivalent to a gradient flow, some sort of gradient flow of KL divergence functional, which can be shown to monotonically decrease the KL divergence with the target distribution. So I want to talk a little bit about the role of this kernel that we used. Turns out the kernel actually defines this, is a part of the, defines this gradient, the functional gradient of KL divergence, but it doesn't actually restrict the solution set of the optimization. So this is very different from the traditional variational inference, which defines a parametric set for your solution. So the drawback for traditional method is that if, assuming you actually already have the ground truth, then the approximation will actually draw it back towards to the bad solution, versus our case, no matter what kind of kernel you use, once you get the true solution, it will stay over the true solution. So just briefly, some of the results. So basically, we tried Bayesian logistic regression. So just briefly go over what I want to emphasize is that if you only use one particle, you already get very good performance. That's because one particle is gradient ascent for MAP. So we also tried deep neural, only one layer Bayesian neural network on UCI data sets. We only use 20 particles. Turns out performs quite well. But again, this is sort of a small scale examples. So now talking about this particle algorithm, so in general, particle algorithms are great because they are consistent as you use more and more particles, but they have drawbacks if you actually have a large number of distributions that you want to inference over. So one example of this is when you do maximum likelihood tuning for energy models, you need to approximate the gradient, and it involves needing to draw samples from the model over and over again at each step of gradient descent, right? In this case, it's really painful to actually do a separate particle approximation at each iteration. That's basically not doable. So the idea is that we can actually amortize inference. So this is a very nice idea that people have been thinking about recently very much. So what we can do is that instead of solving the problems from scratch every time, we actually train a neural network that learns to summarize the dynamics. So in the end, we just need to run through the neural network to get the sample, right? So. And as we update the energy model during maximum likelihood training, we can sort of update the neural network to make it follow the energy model. So just to be slightly more concrete, let's say we have a distribution P, and we have a neural network with parameter eta and random input C. So we actually don't need to know the distribution of C or how the F depends on C. So, and we want to find the parameter eta so that the distribution of the random output X matches with the target distribution PX, right? So the way to do it is actually very simple. based on Stein variation gradient. So what's happening is every iteration, you run through your network with random inputs, and you get a set of particles, right? And then you use the gradient, the Stein variation gradient, which tells you how to update the particles so that the Kell divergence decrease in an optimal way. And then you can sort of backpropagate this gradient into the network. So adjusting your network parameter so that the output moves according to the Stein variation gradient that guarantees to minimize the Kell divergence. So in the end, the update is actually very simple. So basically what's happening, you have that Stein variation gradient, you multiply it with the gradient of the network. So really just backpropagate the Stein variation gradient. So that in this way you can iteratively update your eta parameter so that it fits with the target distribution. So the algorithm that we derived now is actually very similar to GAN methods. What's happening is we have an energy model. The energy model tries to fit with the data by maximizing the likelihood of the training data. On the other hand, the generator, the neuron sampler, tries to draw sample from the energy model, right? And this sample, by definition, should also have a high probability under the energy model. Now, in the end, the sample that you generated is going to be very similar to the observed data. And notice that in this case, the neuron sampler actually only see the samples, the real data set through the energy model. This is essentially the same setup, same kind of setup as GAN have. So we have some results on face data sets. We have so this is when we randomly we sort of do a random walk on the input, a random input, and you can see so it captures the semantic meaning of the images when the glass is off and the color of the hair changes. Just another example when we generate bedroom images. Okay, so we actually compare with DC Gang. So this is on Cepha 10 dataset. We visually don't see any difference. I'm not sure if any experts here can see a difference here. So we check the inception score, which is a score, roughly speaking, tells you how the images looks like a real image. They have around the same result. So sort of roughly speaking, the same thing. We also did another experiment, in which case we used the simulated image as a training set to train a classifier and test it in the real testing data set. In this case, we do find it's better than DC Gang, but I think it's still unclear whether this is some measure. I think it's a still ongoing argument. What's the really good way to evaluate these methods? So some related work. So in fact, we are not the only group which use the energy modeling approach for GAN. That's a work by Kim Banjo, as well as a recent iClear submission by Zai et al., and uses similar amortized maximum likelihood idea for training energy models, right? But use heuristic diversity regularizers or entropy approximations. So that's also this energy GAN paper, which uses energy score function as a discriminator, which is very similar in terms of algorithm, but didn't frame it as a maximum likelihood training. So I'm sure there may be some other work that I missed, so please let me know, because so this idea, I think it's really the right time, and I'm not surprised if different people came up the same idea. So to conclude, we have some idea about how to do sort of log Q-free or wired variational inference, and we used it to turn an old school maximum likelihood training of energy model into a sort of mesh, modern style GAN method. And I think another key message I want to bring is that we are sort of eager about new mathematical devices for linear inference. It looks like this stance method, which has been used in theoretical statistician, seems to provide some new opportunities for new methods. So thank you very much.
Hi, to your right here. Yeah. So this is, it's really interesting, and I find it a little even surprising that it works as well as it does, because my intuition would have been that in high dimensions, that this repulsive force wouldn't really be enough to give you diversity, right? Because high dimensional spaces are so big, and you need just this really enormous number of particles usually to really tile them. So can you maybe help me to understand why it is that this works?
This is a really good question. In fact, I didn't mention. So in this energy model, so this scan paper we did, we actually use an autoencoder to extract the latent variables and then apply a RBF kernel on that latent variable. So that's probably the reason it worked. But I'm not sure if I strictly apply Gaussian kernel if it will not work, because we sort of didn't try that. Might work or not. So the reason is because even if you do a Viterbi tuning, the result is actually reasonable. Viterbi tuning is like you just maximize the mode. That even works. So like probably using good kernel, you can encourage better sparsity, sort of diversity. Yeah.
Great, thank you.
Yeah.
Hi, Qiang, right here.
What? Oh,
Hi.
Hey, Max.
Thank you. Really nice work.
Thanks.
So have you tried to actually sample from the Bayesian posterior of a neural net?
We tried.
And?
So we try to understand if the energy model is good, right? So instead of using a neural network to sample from the energy model, we use a typical MCMC to sample from the energy model. Is that the question you asked?
No, I want to, like, if you take a Bayesian feed-forward neural net, and then you try to apply your method to the parameters of the neural net.
Yeah, that's the earlier example we tried. So we tried a small-scale neural network on like UCI dataset. It works quite well.
And if you make a really large one?
We didn't try it. It will be very interesting to try it.
Thank you.
Yeah. Hey. Well, I didn't actually hear what do you mean use some. Yeah. Right. So right. So the question is, if I understand correctly, is that we have this optimization problem here. And the way we get closed form solution is to set the function set to be a reproducing kernel space. The question is, if I have tried to actually optimize the function, set up phi as a neural network and optimize it. I didn't actually try it. So the reason is that it makes it complex to optimize, because this will be an inner loop. You will get minimax problem. So that may introduce a difficulty. But it could be that because of neural network, it can capture more hierarchical structures. So one approach that could be possible is to use a neural network kernel that may bring the advantage of the neural network while still have the closed form solution as the kernel have. Yeah, that would be possible, yeah.
Let's thank the speaker again.